In this video, I shall present the context of the creation of the Zeroth law of thermodynamics and describe how it renewed confidence in our ability to measure temperature. This context will involve a very brief description of the first three laws of thermodynamics, but we shall study each one in far greater detail later on. The story begins around 1850 when a German scientist named Rudolf Clausius took the law of conservation of energy, which states that energy can neither be created nor destroyed, merely changed from one form into another, and applied it to the idea of a thermodynamic system. This resulted in the first law of thermodynamics, which defines change in the state function internal energy of a system, based on energy flow into or out of the system. It subsequently then led to the definition of a further state function called enthalpy. Following on from initial work by Sadi Carnot on heat engines in 1824, Clausius, again around 1850, began to consider the direction in which processes occur spontaneously. For example, hot objects always lose heat to their surroundings. A cold cup of coffee will never suck heat in from its surroundings to become hot again. These considerations led to the definition of a further state function called entropy and the second law of thermodynamics, which defines it and governs its behavior. In 1912, another German chemist named Walter Nernst was considering the behavior of matter as temperature approaches absolute zero, or minus 273.15 degrees centigrade, the coldest temperature possible. Consideration of the entropy of a perfect crystal led to formulation of the third law of thermodynamics, which led to the definition of zero on the entropy scale, and thus it became possible to measure absolute entropy. It wasn't until around 1935 that concerns about the nature of temperature measurement began to surface. Clearly, temperature and measurement of temperature underpinned every single facet of this new theory of thermodynamics, and yet there was a fundamental issue with the way in which temperature was measured. Consider how a thermometer works. Imagine having your own temperature taken by a nurse in a hospital. The thermometer is placed under your tongue, heat flows from you through a thin wall of glass into a reservoir of liquid, which is usually either mercury or red-dyed alcohol. Thermal expansion causes the liquid to be pushed up a capillary tube with a graduated scale. It is the temperature of the liquid and its ensuing thermal expansion that is used to measure the temperature under your tongue. But at no point does the liquid actually come into contact with your mouth. This quandary led to the formal statement of a new law of thermodynamics. When two objects are separately in thermodynamic equilibrium with a third object, then they are in thermodynamic equilibrium with each other. Whenever two objects are in contact with one another, energy will flow between them until they reach a state of thermodynamic equilibrium. Upon reaching this state, we say that the two objects are at the same temperature. So in other words, this new law of thermodynamics states that when two objects are separately at the same temperature as a third object, they are at the same temperature as each other. In terms of the thermometer, the two objects are your mouth and the mercury or alcohol, and the third object is the glass. Put another way, once the mercury or alcohol level stops moving, the liquid, the glass, and your mouth are all in thermodynamic equilibrium with each other and are all considered to be at the same temperature. Now this might seem kind of obvious to you, and indeed this is probably why no one had really thought to state this law formally any earlier. However, because temperature is such an important concept central to the entirety of thermodynamics, this new law was deemed so important that it required a name that would precede the first three. Consequently, it was coined the Zeroth law of thermodynamics. Okay, so now we have a solid basis for the measurement of temperature. In the next lecture, we shall consider the first law of thermodynamics and the concepts of internal energy and enthalpy.